Now that we've got a little bit of an idea of the arrangement whenever it comes to vector registers and lanes and also being able to load and store things from memory, most of that should probably make a little bit more sense whenever we start talking about the ARM processor and how it does vector operations. But before we get there, we have one more kind of, well, actually two more little bits of business for how these operations are done. Um, I'm going to go ahead and draw this. I'm going to create this array. So I have some sort of an array in memory. It's supposed to be an angle bracket. And this array is, however big it is. Got all these elements. Each one of these little blocks is supposed to represent an element. All right. Now, I've got a vector register. And the vector register is going to allow me to load the vector with these different array elements. Let's say my array element size and the size of my vector register makes it so that I can load 8 data elements into a single vector register. So I grab, let's see, there's 1, 2, 3, 4. Is that 8? 1, 2, 3, 4, 5, 6, 7, 8. Yep. So I load these into my vector register. I do some sort of an operation. Done with it. Want to move to the next group. So I load 1, 2, 3, 4, right? 1, 2, 3, 4, and 1, 2, 3, 4, 1, 2, 3, 4. All right. And do my operation, store the result, and then 1, 2, 3, 4, 5, 6, 7, 8, and I screwed up. But, well, we'll move it. We'll try it again. So this worked really well. So we did the operation. So we do the operation 3 times. Now, let's say that I have an array of a slightly different size, and let's hope I don't do the same thing this time. Because if we do, I'm going to have to cancel and start recording over again. All right, so 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then we only have these 4, so there's only 4 elements here. Well, these 4 elements, I can't necessarily perform the operation like I would, like I had on these first 3. There's another possibility, and this possibility is that I have a small vector. All right, so if I tried to load this into a single vector register, we fell short. And so there's 3 ways of things happening here. Either the size of my vector is exactly divisible by the size of or divisible into the size of the array. There's one here where I have some sort of a remainder. And then there's another one here where the full array won't fill the vector register. So there are 3 different ways that this could possibly be a problem. So let's take a look at ways to handle this. And in fact, one thing that's kind of note is that it is most common that your vector registers are going to have a power of 2 number of lanes. And it is more than likely that your array length is not going to be a power of 2. So really, until runtime, we do not know what the solution is. So our code has to be able to dynamically see which one of these situations we've got. It needs to do this in real time. You can't assume, or at least the hardware, the way the hardware works and the way the functions are set up, you can't assume that we are going to have always this first case. And so there are a couple of ways that we can handle this. First of all, if the vector real length, if the vector's actual length is equal to a multiple of the vector's register length, well, cool. We'll just use vector-based loop and perform the operation as we would. The problem is, this may not have been clear with my little drawing up here, The big problem comes to when it comes time to store the value. So when we come time to store the value, are we going to have these four elements here that were empty, that did not actually have a result in them, but they were part of the vector operation? When we go to store this, if we assume that every array is exactly the same, as a multiple of our vector register size, then whenever it comes to storing, we're going to have a problem there. So if the vector is shorter than a vector length register, well, heck, we can just use a conventional loop. Just do things the way we had always done it. There is the chance, though, and the ARM processor does not do this, but there is the chance that we have something called a vector length register. It is simply a register which identifies the number of elements to perform the process on inside of the vector register. Kind of helps us out, but more often than not, we won't have a vector length register, and we'll have to just perform the operations using the non-vector loop method. Just create a loop as we normally would have. If the vector is longer than the vector register length, then what you're going to do is a combination of 1 and 2. You're going to first either perform, and this is the way we're going to see in the code that we used in the lab on Monday, you're going to either perform a conventional loop on the remainder. In other words, the array elements that if we took it away, suddenly the leftover elements would be equal to a multiple of the vector register length. But you could also use this vector length register. So we start out typically with number 2 in order to clean up or fix the length of our vector so that it'll fit in a vector register. And then once you've made the remaining elements a multiple of the vector register length, then you just go ahead and do number 1. So you start with number 2, then you do number 1. All right. Now, that clears up if we have a register of a particular, if we have an array or a vector that is of a length that's not divisible by the size of our vector register. But we have another issue whenever it comes to the housekeeping or the operation of our code. Let's take a look at this code real quick. This code has, there's not necessarily anything wrong with it. It's just saying something like, okay, what we're going to do is check every single element of our array X. And if that element happens not to equal 0, then we're going to subtract the corresponding element from array Y. Not a big deal, right? Well, the problem is that if I were to put all of X, all the different values of X into a vector register, so X0, X1, X2, X3, X4, X5, and then we'll have our values for Y, right? So Y0, Y1, Y2, Y3, Y4, Y5. I realize this is not a power of 2 number of registers, but that's just the way it worked out. I have a condition as to whether I'm going to perform the subtraction of these guys. I have a condition as to whether that's going to happen or not. Let's see. And I have a condition as to whether I'm going to perform this subtraction or not, and so forth. Now, how are we going to handle this? Well, one of the ways that we can handle it is that we can have a set of flags. So I have 6 elements in my register. Let's create a 6-bit flag. And that really didn't work very well, did it? Let's try it this way. So I have a 6-element flag. So this is just a set of flags. And in some of these positions I have 1s, in other positions I have 0s. And what's going to happen is I can do a conditional execution. for this instruction right here, I can do my compare, and then what's going to happen is this compare is going to populate these flags. And wherever there is a 1 in one of the flags, and so let's just shift this to a different color. So notice that there's a 1 in the first position, so this one's going to get done, right? There's a 1 in the second position, that one's going to get done. There is a 0 in the second position, so that one is not going to get done. There's a 0 in the third position, that one's not going to get done. There's a 1 in the fourth position, so that one is going to get done. And there's a 0 in the last position, which means that one is not going to get done. And so although the operation is still being performed on the vector itself, this set of flags identifies whether or not the operation is going to take place in that particular lane. So notice that we have flags of 0 in the second, third, and fifth position. That means the lanes 2, 3, and 5 are not going to have that operation performed. This guy is referred to as a vector mask control. And just like we've been doing with any of the conditional execution for the ARM processor, this makes it so that we have conditional execution within a lane. Notice that whenever we clear these flags, this sounds kind of funny, but when we clear these flags, it actually puts 1s in all these positions. In other words, it enables the operation to occur in all of the lanes. The condition statements, or the if statements that we were using before, those are actually going to put 0s in the individual bit positions. So once again, clearing the vector mask typically sets it all to 1s, meaning that all lanes are being enabled. Just like with scalars, we can set these flags just using basic operations. It allows us to use any sort of operation in order to set conditional execution later on. Notice that whenever we go back up to here, even though there were 0s in some of the lane flags, some of the flags for the lanes, that still was an execution cycle. So we didn't save any time or any speed by not executing those lanes. The execution, the instruction is still performed on the vectors. It's just whether or not we are storing the result. So it still takes the same amount of time regardless. And what we're going to do next is just kind of show you, well, actually, tell you what, let's do one more slide. I know that you all are really into this. Let's do one more slide. Let's talk about basic memory operations. Basic memory operations are going to be a little bit more complex. We've talked about interacting between memory, the cache, and the processor. Well, whenever we add this idea of loading these huge vector registers, and when I say huge, it's 256 bits, 128 bits, lots of bits. We need to change or modify the interface between the processor, specifically the registers, and the load and store units that are interacting with the cache. Most of the time, we have these memory systems that have multiple independent banks in order to give us the opportunity to load things or store things multiple bytes in one clock cycle. It also means that we might not have things loaded and stored in exactly the same order that they were, would appear in, say, the array or appear in, say, our code. But what we're going to end up with is a great application for all those extra transistors that Moore gave us in Moore's law. And we're going to create these memory systems that are going to allow us to do large blocks of data back and forth between the cache and the registers, or the cache and memory, in order to support vector operations.